how does what?
You was going to talk about the gold plated record.
Oh, the gold plated record. I'm sorry. I totally. Yeah, I totally blanked on that. I'm sorry. You know more about it than I do? Maybe you know something more about the track listing? No? Yeah. I'm going to say around 12 hours or so each way. Yeah, that's just a rough, I'm not absolutely sure about that, but that's, well, the thing is Pluto's about 40 astronomical units out, so if you figure 8 minutes per astronomical unit for light transit time, for example, we're 1 astronomical unit from the sun, takes us 8 minutes to receive light from the sun, so you just do the ratio. So it'd be 320 minutes, or about 5 hours to Pluto. And I think we're talking 2 or 3 times farther out than that, so that's why I'm getting to something like 12 hours. Yes? Do I believe in aliens? Of course, who doesn't believe in aliens? And whether they come here, well, the thing is, aliens, you talk about two different questions. Have they ever been here? And is there any life in the universe? You know? Well, it's hard for me to believe that there's no other life in the universe with everything that's out there. I mean, if it turned out that we were the only life in the universe, then I'd probably become religious at that point. That would be so incredible that we were the singular point in the whole universe of life. But, you know, even if there is life, we may or may not find out about it for a long time. Now, whether aliens have come here or not, no comment. What can I say? Anything else? Okay. Now we move on to chapter 7, the Earth, our wonderful, lovely habitat, which we're slowly destroying. Again, of course, the only planet with a full water cycle occurring and a weather cycle of the type that we see. Here's a shot from Apollo 11 of the Earth over the moon, rising over the limb of the moon. This is taken from orbit. And you can just see immediately the contrast between the desolation that we really find everywhere else in the solar system compared to this incredible oasis that we see on Earth. I mean, if you think about traveling through interplanetary space, and you compare it to traveling through a desert or something like that, in deserts occasionally there are oases, right? Well, if you just look at the distances involved, this is a much more unique oasis by a factor of like 1 billion or so, compared to anything you might bump into in the desert, because it's the only habitable point within light years that we know of. You know? There's no contrast like that if you talk about the most inhospitable place on Earth. So Earth is really unique, not only in our solar system, but in this particular area of the galaxy that we know of, compared to this kind of desolation that we see not only on our moon, but really everywhere else in the solar system, as far as we know so far. All right, so when we talk about the planets, we're going to talk about their bulk properties, and one of the main things, as I mentioned so far, is this idea of the density. Because the density, which is like the average density of the planet, is going to tell you the most basic facts that you have about the composition and structure of that planet. That's the most key number. To calculate the density, we're going to use a standard formula for the density, which is that we take the mass and we divide it by the volume. Now, most of the planets are pretty darn close to spherical, so we can use our trusty spherical volume formula, which I'm sure you all have memorized. 4/3 pi r cubed. Now this r with the cross here represents the radius of the Earth. So this is just the volume of the Earth we're talking about here. And the radius of the Earth, as has been known for thousands of years, is about 6,300 kilometers. So we pop that into the formula, and we get about 1 trillion cubic kilometers, right? A billion is, no, it's actually a quadrillion, right? A billion, no, it's a trillion, yeah. Billion, 10 to the 9, trillion, 10 to the 12. Take that out of the video, right? They're videotaping all my lectures.
Nope.
Cut out the bad one. But yeah, about 1 trillion cubic kilometers. What we're generally going to use is cubic centimeters, 10 to the 27 cubic centimeters, where a cubic centimeter, of course, is about the size of a sugar cube or something like that. Most of the mass that we see is contained in the interior, naturally, the rocky interior, rather than the surface or the atmosphere, the Earth. And the interior is completely dominant compared to this very thin layer of atmosphere around the edge. Now one could ask, how do we even determine the mass of the Earth? The mass of the Earth is actually determined by using this Newtonian formula for the gravitational acceleration. Because we know that the prescription for the Newtonian gravitational force is that the force is equal to the universal gravitational constant times the mass of the Earth times the mass of whatever body we're calculating the force for, divided by the square of Earth's radius. So if we were standing on a scale, on a spring scale, standing on a spring scale, you're compressing the spring, and it's the force of gravity that's compressing the spring and making the dial needle move to wherever it's going to move. This is the force that does it. So in that case, this is the mass of your body right there. And the force scales with the mass of your body. It's proportional. And by the way, the negative sign is there because it's an attractive force. That's what the negative sign is there. Now, the acceleration is related to the force because we always know that F equals ma. And this little m here is, again, the mass of your body. So what I'm trying to compute is the acceleration of a body near the surface of the Earth. So what you do is you relate these two formulas for the force to each other. This is the prescribed force from gravity. And this is how the force is related to the acceleration. And if we combine these, we get that the acceleration is independent of the mass of your body because these little m's cancel out on the two sides. The acceleration only depends on the mass of the body and the square of the radius. So from observations of the acceleration, like if I drop my trusty cheap laser pointer, it accelerated a little bit. If we measure that acceleration, then we know what this a is. If we know the radius of the Earth and the g, we can calculate the mass. Anybody know who this is? Not, I thought it was like Snickers or Skittles. Right, sorry. Right, I mean, yes, so let's see now. I don't really remember how this works anyway. This is very dated, by the way. This is very vintage whole thing here. But that's really dated. Does anybody even get that? This is like from quite a while ago. Oops, there goes gravity. Nobody gets that anymore? A few people still do? Okay. Whatever. Okay, well that's what closes the whole circle on this. It really brings it up to date, because that's, of course, MP, right? I don't even have to say it. MP. And yeah, so that's kind of a comment about Snickers. I'm kidding. A little bit old. Okay. So anyway, the mass of the Earth comes from an observation of the acceleration and knowledge of the radius. And so what this means is that we can calculate the mass of any body if we can see how things are accelerated as they pass by that body. In the case of the Earth, we have other ways of calculating the mass because we happen to live on Earth, so we have knowledge of its density and volume. But if you're talking about another object, like another planet, there's lots of planets we can't even land on, like Jupiter, for instance. But when we fly by Jupiter, we can detect the acceleration that's caused on the satellite that flies by Jupiter as it's affected by Jupiter's gravity. And we know how far the planet, the satellite is away from Jupiter, so we can calculate its mass that way. But the bottom line is that the mass of the Earth is 6 times 10 to the 27 grams. Now this average density I was talking about gets formed by taking the complete mass and dividing by the complete volume. Remember, the volume was pretty big. It was around 10 to the 27 grams. So these are sort of comparable numbers. So if we take the ratio, take the mass, divide by the volume, we get this average density of Earth, which is this funny little Greek rho symbol with the cross to indicate that it's the Earth. And we take 6 times 10 to the 27, divide by 10 to the 27, the big numbers cancel, and we get about 6. This is just rough. It's maybe more like 5.5 or so, but it's in the ballpark. The average density of the Earth is around 5.5 to 6 grams per cubic centimeter. So if we take the entire Earth to do this, that would be the average density. What we're going to find is that even though this is the average density, on the surface of the Earth, the density is actually lower than this. And in the core of the Earth, where most of the iron is, it's actually more dense. So this is, again, just sort of an average value. But it does help to indicate that the Earth is, of course, a rocky body. because the density of surface rocks is about 2 to 4 grams per cubic centimeter. It's a little more dense than that. It's much more dense than the density of water. And so what we conclude is that the Earth is basically rocky, but there must be a dense core on the inside, right? Because the average density is 6, but the surface rocks are only 2 to 4 grams per cubic centimeter. So if the entire Earth were made of what we see on the surface, then its average density would be 2 to 4 grams per cubic centimeter, but it's higher than that. So there's got to be something in there that's more dense. So that density figure is an indicator that there's a dense core inside the Earth. And remember that the density of the Earth is similar to the other terrestrial planets, particularly Venus and Mercury. So right away we can say Venus and Mercury probably have dense cores too. Mars actually has a lower density, may not have as dense a core. The Earth is also spinning. This creates an equatorial bulge, which is much less dramatic than what I've indicated here. Only about 40 kilometers. This is because of the centripetal force associated with the spin of the Earth. Now remember, the Earth's actual radius is over 6,000 kilometers. So a bulge of 40 kilometers is much, it's only about 100th of a percent or thousandth of a percent. So the Earth is basically really close to spherical with this slight equatorial bulge.